Taking attendance in a 400-person lecture hall requires a significant sacrifice of instructional time. When an instructor relies on manual roll calls, we inevitably encounter two logistical bottlenecks: the sheer duration of calling hundreds of names sequentially, and the constant vulnerability to proxy attendance. We can bypass these bottlenecks entirely by shifting from a serial administrative task to a parallelized computer vision pipeline. Instead of calling names one by one, an instructor captures a single wide-angle photograph of the entire classroom. The system ingests this image and instantly outputs a fully verified automated attendance log. Shifting to batch processing recovers lost lecture minutes. By automating the verification of an entire room in a single operation, we remove the human data entry bottleneck from the start of every session. Building this pipeline requires a specific stack of libraries and frameworks: Python for the backend logic, OpenCV for image processing, InsightFace for neural network-based facial recognition, NumPy for vector operations, and Streamlit for the user interface. This flowchart maps the chronological path of our data. The system ingests the upload, isolates faces with OpenCV, extracts biometric features using InsightFace, and finally passes the structured data to a Streamlit dashboard. By triggering OpenCV and InsightFace across all detected regions simultaneously, the architecture executes low-latency analysis, completing the verification of an entire lecture hall in seconds. Combining discrete back-end computer vision libraries with a lightweight front-end framework yields a cohesive biometric verification system that is ready for immediate deployment. Before the system can verify attendance in a crowded room, it requires an authoritative baseline to check against. This baseline is built during an initial enrollment phase. The system ingests a standardized front-facing ID photograph for every registered student. In this deconstruction, the InsightFace model strips away superficial pixels, like lighting and background, evaluating facial geometry to output an array of 512 distinct numeric values. This deep feature embedding array serves as a highly dimensional, unique mathematical representation of that specific student's face. The database never actually stores images of human faces. It exclusively holds these dense numerical vectors, establishing an objective baseline for all future matching operations. With the database populated, the core mechanism activates at the end of a lecture when the instructor uploads a wide-angle photograph of the entire room. The first step is dense face detection. The algorithm sweeps the high-resolution file to identify and map bounding boxes around dozens of distinct subjects simultaneously. Unlike the perfect lighting and frontal angles of the enrollment ID photos, a live classroom is an entirely unconstrained environment. Notice in this tight crop how the model handles spatial extremes. The Retina face detector is specifically optimized to locate faces, even when they occupy a very small pixel area in the back row. It resolves partial occlusions, isolating visible geometric features, even when a student's face is heavily blocked by the person directly in front of them. The system handles harsh window glare and deep shadows because the feature extraction process is trained on high-variance lighting datasets. It ignores absolute pixel intensity in favor of geometric landmarks that remain consistent under uneven illumination. Focusing on geometric invariance rather than raw lighting allows the crowd architecture to accurately identify individuals sitting at the extreme edges of a high-contrast room. Once bounding boxes are mapped, the system applies batch alignment to normalize angles, extracting a new 512-dimensional embedding for every detected face in the crowd. During the live comparison phase, the newly generated live vector scans across the permanent biometric database, searching for its closest mathematical counterpart. The system uses vector similarity matching to measure the exact mathematical proximity between the live classroom face and the enrolled ID face. To prevent false positives, we enforce a strict confidence threshold. Scores satisfying this metric trigger a green verification gate, logging the student as present. Conversely, scores falling below the line trigger a yellow warning gate, prompting manual instructor review. By rigorously defining these mathematical boundaries, the pipeline ensures ambiguous data defaults to human review, preserving the absolute integrity of the final attendance record. Deploying biometric computer vision inside an academic institution introduces critical constraints regarding data privacy and security. To strictly satisfy these privacy constraints, the architecture is designed to process the unconstrained classroom photograph entirely in memory. In this secure pipeline, the system extracts the 512-dimensional vectors from the live image immediately upon upload, passing only those irreversible numbers into encrypted storage. Milliseconds later, the crucial final step occurs. The original source photograph is permanently wiped from the system cache. Data privacy here is not a software afterthought. By immediately replacing ephemeral, personally identifiable imagery with irreversible mathematical representations, security is structurally guaranteed. To make this complex back-end processing useful, we have to surface the data through an accessible front-end user experience. The moment the batch processing concludes, a Streamlit dashboard dynamically generates and updates the final results on the instructor's screen. This dashboard layout provides immediate clarity. Instructors can view macro-level analytics through summary cards detailing total enrollment, faces detected, and present versus absent counts. Below the high-level metrics, a detailed tabular log isolates unverified or missing students, clearly prompting the instructor exactly where manual intervention is required. A sophisticated computer vision model is useless if it is completely inaccessible to end users. Deploying a rapid UI like Streamlit bridges the gap between theoretical deep metric learning and practical real-world utility. In mere seconds, a highly tedious administrative chore is reduced to a single wide-angle photo upload. As this flowchart sequence highlights, the data moves seamlessly from image upload to dense detection, batch encoding, database matching, and finally, a permanent record. By integrating deep metric extraction with an accessible interface, this architecture replaces the friction of manual tracking with a process that fits into the natural rhythm of a university lecture.